Okay, can you hear me now?
I can hear you.
Okay, good. So I would make just one point, and it's related to these average overcouplings. As Douglas just said, when we have two field theories and we couple them to each other, it is natural that we should allow wormholes. So here are the two boundaries. We are coupling them to each other. And then it's natural to develop wormholes between them. And the wormhole geometry should not be forbidden. And in some cases, there are strong indications that it is actually needed. Now, I think this is particularly natural in cosmology, where we can think of this space as a late time slice in our universe. And then we are averaging, or we're summing over, if we think about the Stringer-Keldysh formalism, we are summing over the possibilities in the future of our universe. And so it's natural in that context to expect that there should be bracket wormholes. So wormholes that connect the bra and the ket geometry, wormholes that connect the geometries that connect the bra and the ket. And so we could live in a universe where ensemble averages are very important and are very important perhaps to determine the actual state of the universe. This is just a vague comment. Thank you. That's all.
Thank you, Juan. I guess our next contributor is Ahmed. I hope you're there somewhere.
Yeah, I'm here. I'll try to share my screen.
Yes, you've succeeded.
Okay, do you guys see this?
Yes.
Okay, so thanks for the chance to participate. So what I'm going to talk about, or what I'm going to make, are a few comments regarding the experience of an infalling observer, and in particular the question of whether the island formula removes the firewall or not. So here's the island formula. Can you guys see my cursor? Maybe. Okay, so here's the island formula on the left-hand side. And so the thing that I wanted to say was the space-time diagrams featured in many of the talks. They come in as leading to certain computations. For example, the usual semi-classical picture of an evaporating black hole is something like the leading saddle of trace of the density matrix of the radiation. You can think of this as function of the entire system. Another is, another space-time is what appears for the Renyi calculation, which near n equals 1 is precisely the original semi-classical space-time, but now with these branch cuts and branch points. This observation that near n equals 1, this geometry is the same as the original semi-classical space-time, is the origin for why the matter entropy in the island formula is evaluated in the semi-classical state. My worry now, with regards to the final question, is that these semi-classical spacetimes, at least from sort of a literal perspective, they're not sort of predictions of what the actual spacetime is. Rather, they are representations of the calculation, and in particular here of the entropy of the radiation. To conclusively answer this question of whether there's a firewall or not, we would need to do two things, at least it seems to me. First is to identify the operator that builds the firewall, something like a firewall number operator, and then compute its expectation value by the path integral. And then just see what the path integral gives. And I guess the one hope would be to show that the semi-classical saddle is the one that dominates for this operator. And then we would declare victory. So that's all I had. Thanks.
Thank you. I guess next is Netta Engelhardt. Are you there?
Yeah, I'm here. So I already had a chance to talk about my perspective earlier in the week, so I'm going to be pretty brief. And just a couple of points that I think are very important for us to think about. The first is something that Douglas has already mentioned and has come up a couple of times, which is trying to address what the gravitational path integral is computing in higher dimensions. So I think we're not supposed to worried about it in JT gravity, in the sense that things make sense. It makes sense that it might be an ensemble there, but in higher dimensions, we're talking about n=4 super Yang-Mills. We would like to understand better what we mean by an ensemble average. Is this just a calculational trick, or is this something which is actually telling us something fundamental about the theory or about gravity? And on the same note,
sorry to interrupt, Neta. Sorry to interrupt, but we have a sound problem. So Malcolm perhaps can unmute himself. Malcolm, could you unmute yourself?
Yeah. Is this better?
It was so bad that I would recommend that we let Neta start over.
Okay.
Yeah, Neta, please start over.
Yeah, no worries. Okay, so I was just describing a couple of my own personal opinions on what are some of the important questions that we should be asking ourselves right now. Some of the more urgent questions, such as what is the gravitational path integral of computing in higher dimensions. So I think in JT gravity, we might be okay with the idea that there's some kind of an ensemble average happening, but in higher dimensions, it again was mentioned in previous talks and in Douglas's talk in particular, we would like to understand better what is this just a calculational trick and there's something else behind it, or if it literally is an ensemble of theories, then what is the ensemble, and how is this different from what we've been looking at all along in terms of semi-classical gravity and higher dimensions. Now, on a sort of similar point, this is something that I mentioned very briefly at the end of my talk. When we're talking about ensemble averages and the contribution of replica wormholes, we can also look at something like the free energy, which is possibly the simplest thing we can be calculating. And it really makes a difference whether we're calculating log of the average, ensemble average of Z, or the average of log Z. And I think that there's a lot to be learned from the differences in something as simple as the free energy. And then the final point I want to make, and again, I'm trying to be brief here since I had my chance to talk at this conference already, is I think we really, at least I would really like to understand how to do the calculation that the gravitational path integral is doing for us, just purely on a quantum mechanical level. In particular, so that we can compare the just the quantum mechanical formula for entropy that gives us the page curve in quantum gravity with the calculation that Hawking did, and once and for all really understand the difference between the two. And so this is just my my perspective and where I think we should be going right now. Thank you.
Thank you. Almheiri is next.
It says sharing is paused for me. I think somebody has to allow me to share the screen.
Try now.
Hello?
Try now, Samir.
Yeah, can you still see? Yeah, shall I try to share again?
Yes.
It didn't allow me to share last time. Okay, can you see the screen now?
Yes.
Okay, let me just try to go to view the screen. Okay, so that should work. Can you hear me and see it?
I can
Yes.
Okay, great. In my talk today morning, I was just talking about what fuzzballs do and the perspective we get from there. And I do think that gives us a complete picture of what should happen with the information paradox. But what I would like to do in a couple of slides here is share my thoughts on what I think the other approach through wormholes and the recent work on the page curve seems to be doing.
Samir, we can only see a little bit of your presentation. Could you make it full screen? Or?
So it is full screen on my side. How does it look?
It's not on ours. Maybe.
Yeah, it was full screen on my side. Do you see the top line saying, what does the Gibbon-Hawkins tell us?
We do, but it's just a window on your screen as opposed to the full screen.
Yeah, it's not maximized.
Yeah.
So I did maximize it and somehow it's not maximizing over there.
Maybe
I only
unshare.
see half of except at the S.
It's showing the wrong window.
That's right.
I'm sharing the wrong window? Okay. So I can just-
Desktop should be, yeah.
I'll do a stop share and start sharing again.
Yeah. That's it.
Okay.
Perfect.
Much better.
Okay, does that look fine now?
Yes.
Thank you. Okay, so I'm just going to share with you my thoughts on what I think the recent calculations are telling us as far as the information paradox is concerned. And for that, let me just go back to what the Gibbons-Hawkins calculation of entropy told us 30 years ago. So here is the kind of disk geometry that we use to do the Gibbons-Hawkins. It's a cigar across a sphere, and you can add handles to it. In principle, they are suppressed, but then whatever answer you get from here is always a finite answer, and then you can use it in a thermodynamic relation to find a Bekenstein entropy. So now you might think that you learned something about the entropy of black holes, but that is not the puzzle. The puzzle is that if you actually go to the Lorentzian section, then you find an infinite number of states with the same energy equal to m, so that the z actually becomes infinity. And so that's, of course, clear. You can make those states explicitly. This kind of slice with just in the Eddington-Fickelstein diagram just keeps going on, and you can put both positive and negative energy quanta on it. You automatically generate that kind of states if you feed and evaporate a black hole for a long time. And in fact, clearly the entropy is infinity. So a version of the information problem is then just this. What you get from the Euclidean calculation is a finite number, but what you get from here is not. And so then what are you supposed to do to solve the puzzle? Well, you have two choices. In the full quantum gravity theory, you can either go and show that this Lorentzian picture was completely wrong. A small correction to it wouldn't change it because the bags of gold problem is also robust to small corrections. Or you can actually say, no, I can't change that picture. And then I accept that S-Beck does not give me the total entropy that can be stored inside the horizon. I can store an infinite amount of entropy. And relativists like Ward, Jacobs, and all sort of agreed you might get remnants of baby universes. S-Beck is not the entropy of the black hole. But what you cannot do is say that the simple Gibbons-Hawkins calculation you did, if it spit out a finite answer for you, you can't say that semi-classical gravity was clever enough to tell us the black hole can have at most S-Beck worth of states, because that is begging the question. So I think that people would basically agree with. And I just want to compare that with what the kind of calculations we are doing now. So again, we start with the Gibbons-Hawkins disk, but now we cut a slit in it, we put states psi and psi prime above and below and compute a explicit density matrix. You can add handles and do the full thing, maybe in a computer if you wanted, and get an answer. And the question is, whatever answer you get, what does it mean? Well, it has some meaning only when you go back to the Lorentzian section. And here's a picture I took from one of Juan et al.'s papers. And the Lorentzian picture you get actually is the same as what you would get from the CGHS model. The quanta inside go to the island, the quanta outside go out, and the entanglement of the radiation, ascent of just R, the radiation, it keeps growing. And that's not surprising because it is just like the CGHS model, so you should get that. So the way the page curve comes down is that from the point of view of the JT gravity, you actually change the quantity you are actually measuring. Instead of looking at S of R, you look at S of R union I. Now, of course, I'm not just saying that they're just cheating and changing the quantity they want to measure. This was actually supposed to come from quantum effects, which are not in JT gravity. And so with the QES prescription. And so the question really shifts to what is the quantum physics? So because we actually can't learn anything from the classical JT gravity, in my opinion. Really, the burden of the whatever's been done shifts to the quantum physics. And there we are inputting something. There are two quantum physics directions possible. Either you just say that you don't actually have the vacuum at the horizon, don't produce entangled pairs, you have the fuzzball, and then you actually construct those states in string theory. Or you assume you still have a smooth horizon up to small corrections, and then you have all the new effects you like, which then tell you that the interior of the black hole is not like a piece of coal, because there's a piece inside that coal, which is not really inside that horizon radius, and it can be actually affected by things from outside. So the point I was trying to make was that it's not that the semi-classical gravity has been clever enough to tell us anything about the information paradox or the page curve. So this is just the last thing I want to put up here. I think that from what I have seen, we should not say the following, we have computed the page curve and shown that information comes out. That is not what we have seen, because when you go to JT gravity plus scalars, you get the same remnant / baby universes or whatever you would have liked to do at the singularity as you had in the CGHS model. To me, it seems the claim is actually that holography / QES ideas motivate a picture in string theory, which we then input into what we say the black hole is doing. And the conjecture we then make is that new topologies need to be considered in the Lorentzian section. There will be disconnected sectors, baby universes. Inside the horizon is not like a piece of coal because a part of it is connected to the outside. Note, however, that just the fact that the inside is connected to the outside by entanglement is not enough to get any information out. You actually need a physical interaction to move bit from one to the other. So one is also asking for some interactions across what appear to be long distances from the semi-classical picture. So this is just the point I wanted to make. We are actually inputting a physics here that horizon remains smooth. So opposite to the fuzzball physics where you just construct the fuzzballs and you find it's not smooth. Here we're inputting the fact, no, we have a mental picture that we do want the horizon to remain smooth. And then it logically takes you down the path that you actually have a remnant or a baby universe, which in fact it always did. And I think it's a very fascinating picture, though I don't think it's the correct one. But again, it's not a semi-classical gravity has been clever enough to tell us something. It's the QES prescription, which has just motivated a picture. And I think what we are seeing is what that picture is supposed to lead us to. Thank you. That's all I wanted to share.
Thank you, Samir. Next is Jeff. Are you there?
So I hadn't really planned to say anything because I've just given a talk, but let me maybe make a brief comment or two. So I just want to spend a couple of minutes actually just thinking now of saying what to me is the best reason, though it's certainly not a conclusive reason, to think that there is actually a smooth interior and that there's not a firewall or a fuzzball or any other replacement for the interior. And it's not a terribly sophisticated point, but it's really just the fact that Hawking radiation, the Hawking radiation calculation works and gives the right temperature in Lorentzian signature, right? We don't just get the Hawking temperature from the Euclidean calculations to give the entropy. We actually look at the state of interior plus exterior, and we assume that it is in the vacuum state, and then we get this thermal radiation. So that is obviously not a new comment to anyone, but I think there's some value in re-emphasizing it. But there's also, in the context of these quantum extremal surfaces and islands, but there's another thing that the smooth interior picture gets right that sort of, it doesn't seem to me like there's any reason it should be, you should get the correct answer if that smooth interior isn't in some way physically relevant. And that's just looking at the actual, let's draw an island. It's looking at the entanglement between some late time Hawking quanta and all the earlier quanta down here. So, in simple time models, we often like to say that the late time quanta are just maximally entangled with the early quanta. But that's not actually true because black hole thermodynamics is irreversible. So the actual answer is that you have some, it's an entangled state, but it's not maximally entangled. There's a mutual information. But there's an incredibly sort of neat result, at least to me, which is that if you assume everything outside this quantum extremal surface is not encoded in the early radiation, but everything inside is encoded in the early radiation, and then you just look at the change in entropy from moving this extra little mode across to this early radiation, you get exactly the right mutual information. This is a quantitatively exact correspondence, and it really just always happens just because this surface is quantum extremal. Yet, the reason we're wanting it to be quantum extremal has absolutely nothing to do with any calculations you give it that. So it just seems to me that if this whole region is just totally fictitious and just a sort of coincidence this calculation works, it's very mysterious why on earth that exact, there's like the exact correspondence between the mutual information here that we get from unitarity and the mutual information between this mode and these modes in the island region should be exactly the same. That's all I have to say.
Well, thank you. Next is Surat. Hopefully there somewhere.
Surat? Surat, are you there?
Sorry, I'm here. I'm just not being able to share the screen. Now I can share. Yes, thank you. Thank you. Okay. Can you see the screen?
Yes.
Okay, great. Okay, so I'll just try and be. Can you? I hope I'm sharing the right screen.
Yeah, it's not.
Oh wait. Yeah, just 1 second. I shared the wrong screen, I think. Now is it full screen?
No.
It is not.
You're not sharing?
I'm not sharing at all?
No.
Okay, 1 second. Let me try again. Now am I sharing?
Perfect.
Okay, great, fine. Okay, so I'll also try and be very brief. I just wanted to address some of the questions that actually came up in the chat that I couldn't address. In the talk, I tried to argue that all the information that's available on null infinity is actually available on its sparse boundary. And one of the points I tried to emphasize was that this is not an abstract result, but leads to a concrete protocol for extracting information near infinity. There were some questions in the chat about whether this works in ADS. So I just wanted to explain how it works very beautifully in anti-de Sitter space as well. And the story is as follows. So I'm going to simplify a little bit, but the essential story is as follows. Let's say we have some astrophysicists who live in some global state G, which is the state with a red ball, and they want to determine if it is the state F, where F is some other state. And there were questions about whether G and F could be related by a global symmetry, and they could be in this example. And just for simplicity, I'll assume that F and G are both low energy states. And it's clear that in a local quantum field theory, these astrophysicists have to go into the bulk and determine the shape of these bumps and see and check if G is the same as F or not. But the point is that in gravity, they can do this purely by acting with local unitaries and by making measurements near the boundary and in a very small time interval from 0 to epsilon. And the protocol is as follows. Let's just assume for a second that both these states are orthogonal to the vacuum for simplicity. So the first step is you can find an operator, it's Hermitian operator as we discussed, which acts on the vacuum and creates the state F. You're not allowed to act with the Hermitian operator, but you can act with the unitary operator e to the IAXF. And after that, you just measure the Hamiltonian and you count how many times you get 0 up to second order in this parameter A. So this is a completely allowed process in quantum mechanics for these observers. And then you just compute what the result of this experiment is. And you see the first unitary change the state in this way. And after you measured the number of times you got 0 for the Hamiltonian, you see the second order, you immediately get this overlap between G and F. So this is an example of a process that would have been impossible to do in a local quantum field theory by these astrophysicists, but can work completely explicitly. And even if these states are related by a global symmetry, one can determine if they're orthogonal or if they're not. It's by extrapolating these kinds of arguments, that one comes to the conclusion that the information is always available outside the black hole. Of course, once you start going to black holes, these operators, these unitary operators become more and more complicated. And so then the questions become more subtle. You can't find them explicitly, whereas for low energy states you can. But I think the interesting question, which I'd like to focus on, and I'll end with this, and I don't know the answer to this, is a question of whether it is easier to recover information after evaporation than it is to recover information before evaporation. And I think the small black hole is an instructive example. So if you think of the small black hole that forms and evaporates in anti-de Sitter space, you can ask just from the conformal field theory, what is the complexity of the correlators you need to measure to determine the microstate? So before the black hole forms, it's very low. You can probably determine the state of the dust using some 2-point correlators. After the black hole forms, you need very high point correlators. You need S-point correlators, which you need to measure to accuracy e to the minus S. But the important point is, even after the black hole evaporates, you need very high point correlators. In fact, you need higher point correlators because the Hawking radiation has larger entropy, and you need a larger accuracy to determine what the state is. Now, I want to emphasize that this is not a watertight argument because small black holes are very atypical states that we don't understand well. But I think it's an interesting case to consider. And I think it might suggest, in particular, for the case of black holes evaporating in flat space, that if we think of these two nice slices, this one that bends down and this one that goes up and collects the Hawking radiation, it's not necessarily easier to recover the information by making measurements in the green region than it is by making measurements in the red region. So I think the small black hole example is an interesting example to think about. Okay, so I'll stop there. Thank you.
Thank you. Carlos is next.
Thanks very much, but I'm going to pass so we have a little more time for discussion.
Okay, then that makes Andy next. Andy, are you there?
I am there. Can you hear me?
Yes.
Loud and clear.
You got my screen?
Got that too.
Great. Okay. So it's the only one. So in 50 years of discussion of this, there's been remarkably little agreement on anything, and including even what it would mean to solve the black hole information paradox. So I am going to present my view of what it would mean to solve the black hole information paradox, which probably not everybody will agree with. But first of all, I'd like to say that there's two parts of the paradox: how the information is stored, that is accounting for the Bekenstein-Hawking entropy, and how it gets in and out. It's like what makes up the chips in your computer and how it's connected to the internet. They're different but closely related. Secondly, I would say we should not be allowed to make it's a bottom-up problem because we want to understand the black holes in the real world. And we're not allowed to make specific microphysical assumptions such as string theory or so on, but general ones I would view as okay. You could assume symmetries. My favorite example is Boltzmann, who derived the laws of thermodynamics from statistical mechanics, and he had to assume something which was then very controversial, molecules, but he didn't have to make a very specific assumption about the behavior of molecules, just very that there was a smallest piece. I would also view the idea that you should add Euclidean terms in the path integral. That's fair. But general types of assumptions, just not very specific microphysics. I would say we would like to get a microscopic derivation of the Schwarzschild entropy and the universality of the area, which also applies to cosmological horizons, and the log corrections, which also should not depend on microphysics found by Eshot-Sen. And here, the kind of example I have in mind, you say, how can I have a microscopic derivation without microphysical assumptions? Well, I think we have a kind of example in mind of BTZ black holes in ADS3, where we just have to assume that we have a consistent completion of quantum gravity on ADS3, and it is unitary and local and all that. And then we have a conformal field theory. Maybe we have to assume modular invariance and more properties, but general properties. And then we can understand the counting of the entropy without ever knowing the details. We don't have to know it's ADS3 times T4 times S3. We just have to know the ADS3. And we would like something similar for the information flux at Scribe Plus, which everybody is guessing is the page curve. To test our understanding, that should have log corrections because the entropy law, area entropy law does. We'd like to be able to control it well enough that we can compute those. And finally, I would add, there's no guarantee that this is possible. In fact, when Gorman and I first computed black hole entropy from string theory, it depended so much on the 2 pi's and the dimensions of moduli space and properties of algebraic geometry and so on. We were convinced that you needed a microscopic theory to get the entropy right. But later we realized that it all came from holography and general properties, that it was guaranteed to work. So it could happen that to answer this question, we have to find the theory of everything first. I think most people probably agree to me that it's reasonable to try to solve this problem without doing that. Anyway, so this is my brief summary of my view on what it would mean to solve the black hole information paradox.
Great, thank you, Andy. Last but not least, is not there is a real question.
I'm here,
Eddie.
and with your electronic permission, I'll share my screen and say a few words.
Please do.
It says, okay, now maybe I can do it now. Let's try one more time. Share screen. Share. All right. Can you see that?
Yes, it's perfect.
Okay, great. It is perfect. So I'm mostly going to do some cheerleading given the late time and the short time. But this is kind of my picture of where we are. I think this is a very exciting time for talking about black hole information. I feel like before the discovery of replica wormholes, there were some thoughts, there were some ideas, but it was a lot of feeling around in the dark without really a guiding principle. And I feel like the discovery of replica wormholes has at least turned on a lamppost that gives us an interesting place to look for answers to even some of the questions that Andy was talking about. In particular, we learned that the gravitational path integral, something that we thought we had some idea how to work with, at least at the semi-classical level, still has a lot to teach us, again, even at the semi-classical level. So it's sort of clear what to do in the near future. We should go to this lamppost and we should dig into the replica wormhole calculation as much as possible. And so that's what we need to do. And I think it's going to keep us all busy for quite some time. And it's been very interesting that doing so has already suggested that there's a lot of interesting physics at play. Space-time wormholes, baby universes, possibly dualities involving ensembles, et cetera, et cetera, et cetera. And I'm not saying this is the final answer yet, but there's a lot more things to explore. Now, the thing that I am personally the most excited about that has appeared in this process is the idea of what I'll call novel null states. And I'll say just a few words about that. So the basic idea is, very briefly, that the replica wormhole calculations themselves really suggest that the gravitational path integral provides a sort of dynamical mechanism to enforce entropy bounds, which means that even if you write down some setting where you've tried to put more states into a black hole than its Bekenstein-Hawking entropy, the actual entropy appears to be bounded by the Bekenstein-Hawking entropy. That's what the replica wormhole calculations seem to suggest. I'll mention that this idea that the Bekenstein-Hawking entropy is really a bound, of course it's an old idea, but you can make an argument for it just using the gravitational path integral under the assumption that the path integral defines a positive definite inner product for the states in the theory. And I'm not going to review that argument now because I don't have enough time, but this is one of the things that came up in a recent paper with Henry Maxfield, and it's sort of related to the ideas of Daniel Jafaris from a couple of years ago. And I wanted to mention that there's a general argument, but in particular, Henry and I looked at a toy model where you can see this come about from non-perturbative gravitational corrections to the inner product, which have the property that they take states that without the coupling to gravity would have been linearly independent, and so you would have thought of them as completely separate, and they generate linear dependencies. So it's a novel, exciting property that I do not fully understand, but I would like to understand much better. And calculations in JT gravity show evidence, I think, of similar behavior. So that's a weird thing, and I didn't explain all the details, but I'd like to just illustrate again what I said. which is really, you can describe a lot of these calculations as you think about having some system of, let's call it matter degrees of freedom. It doesn't have to be really matter, it could be gravitons, but let's call it matter degrees of freedom. And you might first think of it as this blue box where you write it down on some fixed background. Maybe it's a black hole background. Maybe you do perturbative analyses of quantum field theory inside black holes, and you find that, yes, inside old black holes, there can be vast numbers of states that appear to have vastly higher dimension, vastly higher entropy than the Bekenstein-Hawking entropy of the associated black hole. So this is part of the black hole information problem. You know, these states appear to be there, and how can you fit them inside a black hole, which only has a finite entropy? Well, what appears to happen in these calculations is that when you turn on dynamical gravity, this blue box gets compressed until it exactly fits inside the black hole box. That's an interesting mechanism that, as I say, one would like to explore better. It's also a confusing mechanism. It leaves us as physicists rather confused because, of course, if you take a large space of states and you compress it into a smaller space, you can't preserve all the information perfectly. Some of the distinctions between the original states become lost. So this leads to open questions, which is, how do we really understand physics in this environment? What does it mean for observables inside black holes? How should we discuss, quote, what really happens inside black holes if things that without this dynamical gravity effect we thought were completely different, okay, in fact become kind of the same? All right. So I don't really know the answer, but as I say, it leads to interesting possibilities. And an exciting possibility is, as my collaborator Henry likes to say, that everyone's a winner. That in some sense, all of the ideas that have been discussed about how black holes can return entropy, can return information in Hawking radiation are in some sense true. Even ideas where it wasn't returned are true. It may be that information is in some sense lost when black holes evaporate due to entanglement with baby universes. But it may also be that this information loss, it can never actually be observed by anyone outside the black hole, because in super selection sectors of the universe, in fact, the information is returned. So it's returned in every possible operational sense. It may also be true that due to this lack of distinction, or because of this compression inside black holes, due to these null states, some of the things that have been described before as state dependence may in fact be better described as gauge dependence. Maybe this is a way that ER equals EPR manifests itself. And because of this compression and lack of distinction between things that you thought were physically distinct, maybe smooth horizons and firewalls are also gauge related. I don't know. And there's also room in this for final state boundary conditions. There's also room for highly non-local interactions, which relate to other ideas about returning information in quantum gravity. And finally, this all has to do with the inner product of a gravitational system, which you could imagine is related to corrections to the non-perturbative gravitational constraints that people have also talked about. So there's room for lots and lots of ideas, and I would like to understand this structure better. And that's my story. Thank you.
Well, thank you. So I guess what we should do now is just open everything up for general discussion. There are around 456 participants, some of whom must want to ask a question, of which Emil seems to be first.
Yeah. So I had a question, maybe to one, but I'd also be interested in other panelists' opinions. So there was a picture of a sequence of Penrose diagrams of an evaporating black hole, at which the last one was an island that was disconnected from an ADS region coupled to a bath. So I was wondering what that sequence of Penrose diagrams would look like if I just took a small black hole in an isolated ADS and let it evaporate. So just make a black hole by, putting some operators on the boundary that make a small black hole. Now that's supposed to evaporate. And so it seems like the information is still on the island, or is encoded in the entanglement between the island and the stuff which is still in the CFT, because I haven't coupled the CFT to anything. And so it seems like I have a remnant within ADS CFT, and I'm puzzled as how do I get the information out of the remnant.
Well, first of all, when you calculate the entropy, you would always include the whole black hole interior for all times. And so the entropy is 0 for all times, and it manages to be 0 by including always the black hole interior, even after the black hole evaporates. So you can think of the black hole interior as some other baby universe that comes out. So at least from the point of view of entropy, you always have the right entropy. Now, I think your question is more like, what is the right state? How do I figure out what the right state is? Because the state that is outside looks thermal, that is in the ADS region. And I think that's what we don't understand. We don't understand how to get the right state from gravity. Now, it might be that, okay, so the true thing is that we don't understand. Now we can go to speculations that maybe there is effectively some kind of final boundary condition, for example, in the interior that forces that state, projects that interior state onto some particular state, and then we will get a definite state outside. That's one possibility. But maybe there could be many other possibilities. Maybe the singularity is secretly connected with the exterior particles, and there is some some way that the actual state is encoded in the singularity. That might be somewhat similar. So the short answer is I don't know how to get the right state from the gravity picture.
Okay.
Can I make a naive comment on this question?
Sure.
We don't know how to compute the right state, but there's some kind of complicated state that somehow comes out. And I think Emil's question is really, does the region that ends at the singularity exist a month after the black hole is finished evaporating? So you could simply say it doesn't, that there's just a complicated state of the radiation. On the other hand, if you understand in detail what the state is, you could do some complicated measurements on that state. And if you were able to think of just the right measurements, you could probably come up with some that could be usefully described in terms of the picture where you did say that the region behind the horizon did exist. So it's actually going to be really up to you, and depends on what you want to do and what you understand, whether you say that region exists or not after the black hole is evaporated.
Yeah, but in the calculations that are being done, the mileage is being made by assuming that there's some semi-classical region behind the black hole. And in the calculations, the information that's in that semi-classical region never gets out from inside the black hole. It's just sitting there entangled with some radiation quanta that are outside.
True, and a month after the black hole is evaporated, you can forget about that region if you want to. Or you could say it's useful for asking some very special questions.
Well, but then
I think
okay, that the qubits that are stored there have to go somewhere. So where do they go, and how do they go there?
I think there are two things you could do. You could keep the exterior and the interior, and you have some representation of the state, or you could maybe remove the interior, maybe similar to your Donald's remarks about gauge equivalence. Remove the interior completely, and then have a very complicated state outside.
Okay.
Can I make?
Go ahead, please. Go ahead, please.
Okay. Yeah, I think I just wanted to make some comment about comment and the question, kind of open-ended question about what Andy said. What's the information problem, and how information is encoded in the final state of the Hawking radiation? That's probably not necessarily most important thing. It's like dropping a glass, and how the initial state is connected to the pattern of the final glass is on the floor. It's probably not the first one we want to discuss. So from that point of view, from exterior, unitarity, if you believe ADS CFT, is pretty much kind of solved. So the problem with information problem to me is like interior. What to think of interior? For that, a piece of code and black hole is a very, very different object, because if your horizon, if your surface is recede up to the where local Hawking temperature becomes string scale, then it's a chaotic. Everything's chaotic. That's why if you focus on some mode, which is whose energy is higher than Hawking temperature, then you automatically have the structure of the states of thermophile double. Only if it's a completely chaotic across all low energy species. That's not the case for a piece of code. A piece of code, of course, maybe a photon may be radiated, but not a neutrino. Then, of course, you cannot have a space-time picture interior of the piece of code. But the black hole is very special because it's a string dynamics, no global symmetry, everything is distributed. So then at least you have a state after cross-graining, have a thermophile double state, including the Boltzmann coefficient. And then you can also build a Hamiltonian, which is local by doing just usual Lindblad to falling frame. Then the question is also what Ed was saying, by the existence of those operator, which is a very complicated subtle operator encoded in radiation and some black hole softmodes, is enough to claim that that's the observation. Like, so in the end, what's the observables in quantum gravity, or what's the observation? Is it enough to have that kind of algebra? But at least we have a local algebra. So if you believe that if it's a local, then something is enhanced and become classicalized and observable, so still already observable, then I think we have interior. But if you need to have infinite far away decoherence, then you could claim, okay, interior doesn't have any operational meaning. So it's ultimately, so when we are satisfied, I mean, does the existence of local Hamiltonian plus correct states is enough or not? Is my question, which I don't know, because this is kind of quantum measurement question in quantum gravity. That's it. That's all I want.
Does anyone want to comment on that?
Could I say something about Emil's question previously?
Sure.
Yeah, I just wanted to say, I think, you know, I agree we don't have a watertight argument for understanding what's behind the horizon. But I think the question before that is, do we have a good reason for believing that the region behind the horizon is not what is given by the conventional solution? And I'm not sure that we do really, because if one just looks for information recovery, I think that can be done without having structure at the horizon. Then I think something that Daniel pointed out during the main session, I think it's true that if one looks at typical pure states in large black holes in ADS, I think these arguments that Joe Polchinski and Don Marolf gave about state dependence and some of the issues that could arise with that might be the best arguments we have to argue for whether there is structure behind the horizon or not. But once again, I think that should be distinguished from the case of black holes in flat space, because black holes in flat space are not typical states. And so I'm not sure that there is really any good argument we have for believing that the region behind the horizon is not what is given, what we expect it to be. So, I mean, the default assumption I would have is that the region behind the horizon is what is given by the conventional solution.
Daniel, you seem to be next.
Oh, I was just going to comment. I think even in flat space, you can certainly think about a black hole in a typical state. It's just a black hole that you form by collapsing an exponentially complex cloud of Hawking radiation over a time of order m cubed. And then at t equals 0, that should give you a black hole in a typical state. I don't immediately see how to apply the Marolf-Polchinski argument to it, but I feel like this problem exists also for black holes in flat space.
Well, the argument relies on the fact that these, you know, they want the black holes to dominate the ensemble, which flat space black holes never do.
Well, you can define an ensemble where they do dominate, though, right? It's not the thermal ensemble, but you know, just the ensemble of microstates of the black hole of energy E sitting at the middle of space, right? I want to, can I push a little bit on, also on this comment of Andy about not needing to know string theory? I mean, for me, that would be very disappointing, right? I mean, I guess it may be that some aspects of this problem can be understood without using string theory, but I think
I love string theory, by the way, just for the record.
Yeah, thank you, Andy. But I mean, I think some of the conceptual questions that we're running into, like, do you average, do you not average, what happens in typical states? I mean, I guess I would be a little surprised if you don't need some input from knowing what the structure of microscopic quantum gravity is to be able to resolve those questions. I could be wrong, of course. I was wrong about the page curve, but
I guess I just want to say we won't feel we've fully solved it if at some point we have to say the words string theory and that it depends on string theory being the theory of everything.
why? Wouldn't that be great? Wouldn't it be great if it depended on that?
Well, that's a possible outcome. That's a possible outcome. And we sort of thought that's how it was for a while, but now it's looking less, it would be a less powerful outcome.
My feeling is that the current understanding is more or less similar to the Bekenstein-Hawking situation. We knew how to compute the entropy. Now we know how to compute more sophisticated entropies of either, well, the page curve, you know, ensembles and late time averages, etc. But to get the macrostates, we still need the tools of string theory.
But maybe string theory is the only theory of quantum gravity, Andy. So then it's really not, you know, depending on string theory.
Yeah.
I mean, I think if we have just one reasonable theory of quantum gravity where we can resolve the information paradox, we'll already have learned a lot.
Yeah. Also, I want to comment on, Douglas made the statement about wormholes being bad. People thought wormholes were bad. I never thought wormholes were bad. I thought some of my papers that I wrote on wormholes after the first 2 or 3 were bad. And we've been waiting for a better one, the return of the giant wormhole. And maybe it's coming now, the good one, in which wormholes are put to a really good use.
Yeah, sorry, that was pretty reductionist. By the way, Azadeh Malik Najad has had a hand up for a while.
Yes.
Yes, thanks for noticing that. Thank you all for such great talks. I really enjoyed all of your the talks today. I have a very basic question for Andy about the microscopic description for the entropy, which is super charming. So I'm wondering how it's doable perturbatively, like neglecting the back reaction effect. What's missing that we still don't have that the microscopic prescription? And also, it's related to some physics that we don't know yet. So is that physics is just going to show around black holes, or are there any other like parts of physics that it might show up, like early universe or something like that we can check? Yeah.
Well, I don't think that in any of our lifetimes we will understand all the laws of nature, you know, the theory of everything. And it could happen, but I'm not holding my breath. I think we can solve the black hole information paradox in a shorter time scale. And, you know, Ed used to like to talk about alternate planets on which they discovered string theory before gauge theory in gravity. But we could also think about alternate planets where we discovered holography before we discovered string theory. So you could have started with Brown and Hanau, you could have said conformal field theory, it would have all been a little fuzzy, wouldn't have understood it as well. but we could have started trying to get the outlines of it. We could have said something about black hole, BTZ, black hole entropy. We could have started trying to get, it's not very hard to imagine. And indeed now lots of people teach courses in holography in which they never say string theory. It kind of has a life of its own. But it's more of a bottom up than a top down. And obviously both approaches, the approaches have informed each other, and every approach should be pursued. But what I'm hoping for is a kind of bottom-up approach that will give us some picture of what the microstates are, how they come in and out. I think that this recent work is a very inspired guess that extrapolating ideas from ADS holography to flat space holography, and it may help guide us towards a bigger sort of framework and way of thinking about things that does not, the recent stuff, as if it's not patently obvious, there's no assumptions of any string theory. It's all semi-classical gravity and so on, and it seems to know something about quantum information and so on. So, for that reason, I think it has a very good feel with it and goes along with my idea that not my idea, but the idea that we might be able to make a lot of progress on this problem without having to find the theory of everything, which would also be fun. We shouldn't give up on that, but it's not necessarily the same problem.
Yeah, sorry, maybe I asked several questions at the same time, so
yes.
it wasn't clear enough. So my main question was if this microscopic derivation, how perturbative it's doable. I totally agree with, I'm totally happy with the semi sort of classical dealing with gravity, but my main problem is that in that calculations, we are doing quantum field theory in a background with a fixed mass, while the mass is decreasing because energy is extracted from the black hole to produce those particles, and that's my main problem. How much this back reaction effects or this non-linearity sort of are important in this microscope?
Are you asking about my computation with alpha?
No, actually, this is a very basic and naive question. I'm not referring to any specific calculations. I'm just asking about your last comments during this discussion panel.
Yeah. I think you'll have to, if you don't have the complete laws of nature, you have to live with some uncertainty in the equations. And that makes it hard. And you have to be able to derive things using general principles, and sometimes you can get in trouble. If you're a condensed matter theorist, you just may make a wild leap, and then you have an experiment to help you out. But as a high energy theorist thinking about quantum gravitational theorists thinking about black holes, we have this very strong constraint of self-consistency. It's hard to say anything which doesn't become self-inconsistent, that's what we have to go with.
Thank you.
Okay, Daniel, you've still got your hand up.
I did have another comment, but is there anyone else who didn't talk yet who has a question? Maybe you should do that first.
Yeah, I have my hand up, but...
Well, it's true. Henry had his hand up next.
Okay, so I just wanted to get the panel's opinions on where we've gone with the what progress we've made with the original information paradox, which was asking about a calculation for the experiments or experience of asymptotic observers. This seems to give information loss, but there was nothing obviously wrong with the semi-classical calculation. So this is an easier question perhaps than asking about interiors and so forth. It seems that we've got an improvement on that, and semi-classical gravity does give us predictions for asymptotic observers in line with what one calls the central dogma. But the cost does come with replacing that with a new paradox that it seems to, as motivated, for example, by Douglas's talk, that it seems to give us ensembles or baby universes or alpha sectors as the cost. And we now have a paradox because n equals 4 super Yang-Mills doesn't seem to be, it seems to be a perfectly good theory of gravity by itself. So actually the information problem has now been replaced by the factorization problem. And I'd like to solicit thoughts on if people agree with that perspective, or it mirrors something going on in the chat at the moment as well.
I mean, if the question is, I don't think that one necessarily needs an ensemble interpretation to understand these things. I mean, at least if one looks at situations where gravity is dynamical throughout and the information can be obtained from far away, I don't see that necessarily requires us to turn gravity into an ensemble. So I'm not sure that I would think that there's a new paradox that has been introduced. And it seems to me that one of the Hawking's calculation, of course, neglected exponentially small corrections and also neglected the fact that gravity localizes quantum information unusually, which wasn't understood well then. But so I think we have made some progress towards understanding that.
Maybe could I add a couple of thoughts on that? You start by saying that one can think about the black hole from outside. And in fact, in the paradigm that Juan mentioned at the start of his talk, well, from outside, the black hole should look like a piece of coal. So that perspective actually has always not made that much sense to me. I think there's no well-defined question of saying, how does something look like from outside? If you can throw things on it and get things back, yes, of course, you can stand outside, but there is no, you can't even address or ask the puzzle. That thing is part of your space-time, you're interacting with it. So in fact, the puzzle or the issue only comes when you consider everything. If you stand only outside, you can actually say, well, this happens or that happens, it just looks circular to me. So the question again is you have to say, okay, what happens there? And I think the way to phrase the question is, when you take some region away from the black hole, let's say 4m outside or 10m outside, what is your rules there? Are you changing physics or saying it's basically close to normal lab physics, which you can pull out of a condensed matter textbook? Suppose we say it is that, it's normal physics. Then the question becomes, at the horizon, do you have smoothness or not? And I think that is a precise question. I don't really agree with Marolf's idea that everything could be just representations of each other, because there is a precise question. Is there any description in which the local entangled pairs are being produced in the typical state 0, 0 plus 1, 1? If they are, and the member which is outside has now gone to a place which is semi-classical physics and can't be touched, these are all real things. You can make them as precise as you like. And then once you are in here, you have a paradox. So I think you really have to focus on how you're asking the question, but not try to evade it by saying that you won't look at the inside, or the inside could have many manifestations. Once you take into account the pair creation expression, and you also say that outside 10m, nothing is to change, you have to go to a baby universe or a remnant. So at least there are some things we know for sure, which I don't think can be just wished away by language. So I know that Subrat may disagree with that, but let me just make my perspective on that. I think the entire black hole puzzle can be recast without going anywhere near infinity. You can make a tiny black hole at CERN, hopefully one day with 10 Planck masses. You get only 10 quanta outside. The fact that something is very complicated is gone. We just 10 quanta. And you can ask very precise questions in exactly the language that I was saying. And it seems to me that what we have learned from string theory is that microstates just behave like real pieces of coal, and you don't get the entangled states 0, 0 plus 1, 1. They just become fuzzballs, and we were done long ago with that perspective. But if you do want a smooth horizon, yes, there are very many hard things that you have to consider. Okay, so that was my perspective, and thanks.
Can I just respond very, very briefly?
Sure.
Yeah, I think that the first point is I don't think in these notions where you're identifying degrees of freedom, either in the talks that Juan or Jeff gave, or in the description I was giving, that you're ever adding any new physics. You're never adding non-local interactions by hand, which is something I think you also mentioned in your slides. This is just something that naturally comes out of semi-classical gravity just by making a careful analysis. So I think that's one clarification. There's no addition of some interactions that are going to couple the interior and the exterior. The second thing is, I think we all agree that the true description of the wave function cannot be that of 0, 0 plus 1, 1 raised to the power n. So the true ultraviolet wave function cannot be just entangled pairs in n of them. But I think there is an effective description in terms of that, in the sense that there are operators that you can measure which are entangled, but it is still true that the true description of the wave function is very different. It just has one copy of the degrees of freedom at null infinity. But it's true that it looks like you can find effective degrees of freedom that live in the interior, which are entangled with degrees of freedom outside. But I think we all agree that the wave function is not really what the Hawking wave function is. It's not just 0, 0 plus 1, 1 raised to the power n. So those are just two clarifications I'd like to make.
So let me just briefly comment that in fact what you just said is what I do not agree with. I do not think you can make a bit model where there's a true wave function and there's an approximate wave function. This is what you would like. The true wave function does something which actually unitarily gets information out like a piece of coal. And in the approximate one, it looks like 0, 0 plus 1, 1. And also in the approximate one, once you go outside 10M, you touch nothing. So I think you try to make such a bit model, you will fail. But if you do have one, I would like to see that. So I'm really contesting that.
I think in the papers with Kyriakos and so on, we constructed such operators, one of which looked like, so that if you looked at 2-point functions, it looked like the wave function was 0, 0 plus 1, 1. In fact, it looked like that up to very high order and correlation functions. And eventually the description broke down once you measured very high point correlators. So I mean, and we had concrete qubit models where you could take qubits and just find these operators, which were entangled with the operators outside. And I mean, we can discuss this offline, but I think it is possible. I don't think there's any obstruction to saying that for up to p-point correlators, the wave function looks like that, and beyond p-point correlators, the wave function has a different description. This description in terms of 0, 0 plus 1, 1 to the power n just breaks.
So we should do that offline, because I think that is the mistake that you might be making there. 2-point correlators, small point correlators do not actually tell you what the wave function is doing. That is not what one should do from the start. I'm talking about the state, and I'm saying the true state cannot have the approximation where you keep a smooth horizon and get the information out without non-local corrections. There are no such approximations. If you measure few point correlation functions, you're looking at the wrong thing. You cannot come to any conclusions. But we should take this offline. Maybe let's give maybe other panelists to comment on that.
Okay, thank you. I guess Igor is next.
Okay, thank you. Yeah, I just want to make some, sorry if they're superficial, some partly historical comments, because I was one of the few people here who was working on Coleman's wormholes back in exactly 32 years ago. And I want to echo some of the comments that were already made by Andy and Douglas. Basically, I'm not sure if they were thought of as good or bad, but there was definitely a feeling that the theory was built on quicksand. I mean, when you scrutinize this theory because it was built on Euclidean path integral, and that's sort of ill-defined in 4 dimensions. So basically the story kind of fell apart pretty quickly because of Joe Polchinski's objection from the phase of the sum over spheres and stuff. And then, so in these 32 years, the emphasis shifted to string theory, then ADS-CFT. So it's sort of amusing to see this return to Euclidean path integral, albeit in a much simpler theory like this JT theory. But, and I think this was already said by a few people, I'm not sure if we go above 3 dimensions, we have the luxury of just doing Euclidean path integral. And Coleman's theory is an example of that. So I would certainly hope that, so since this whole ensemble story is also a bit, there are questions about it, you know, I would certainly hope that there is a way to understand page curve in theories without an ensemble. And even in low dimensions, there are examples of something like holography without an ensemble. For example, the duality between two-dimensional string theory and matrix quantum mechanics. Of course, it's not what we want yet because we don't understand black holes in that theory. But I guess the question I have is there a way to understand any of it without the ensemble, even in toy models, without higher dimensions? Like, let's just go to some model of two-dimensional dilaton gravity plus stuff. I mean, I feel like we should still strive towards understanding without the ensemble, but would be curious to hear what people think.
I feel that the calculations of page curve could be done without the ensemble. It's just the other more sophisticated other calculations, like the one that Douglas said, maybe in a complete theory, in a string theory, maybe they might give a different answer.
Yeah, I think there's a sense in which a theory that didn't have an ensemble would necessarily need to be richer than one that does. Like the simplest theories naturally end up being ensembles. And it may well be that in higher dimensions and in richer theories and string theory and so on, then you don't get that. But the toy models where we can calculate the most tend to be ensembles, but I think there's a lot of effort going on now to find toy models that are not ensembles. See what happens with that.
I guess an issue with the JT model is that it's not UV complete, right? So if we come up with a sort of top-down model, even in low dimensions, that may be totally free of the ensemble issue, right? So
can I elevate a point that was in the chat to maybe get some people to comment on the questions that were asked there? This is related to this issue of how you would restore factorization of the partition function for something like n equals 4 super Young-Mills theory, or any case where you have a single unitary theory describing a gravitational system. And I guess I'd like Douglas's perspective on that, or any of his collaborators or anybody else. But my understanding is that we would need additional contributions that basically restore factorization. And it seems unlikely to me that those could arise from a geometric calculation where we still see a smooth horizon. But I think that would be the challenge. If that could be done, then it's in that setting that we could ask how the horizon can be smooth in a unitary theory.
I feel like I've said enough about this already, but I'm not sure. I'm quite curious to hear what other people have to say.
I should also perhaps point out that in a theory like a 2,0 theory in 60, not only do you like to restore factorization, but you better have the same answer as you know, square of the partition function. So what you would need is something extremely fine-tuned, so that you get the answer as if there were no other contributions apart from the standard semi-classical ADS 7 geometry.
Maybe I could comment briefly or tangentially on what Rafael was saying. So indeed, I don't think that if we just look at normal string theory, look at for the eigenstates, nothing ensemble averaged, well then I think the horizon is not smooth. That's the fuzzballs you get and it solves the puzzle. I also am not sure that there is a good sense in which you can average over microstates and thereby get something smooth. So what I'm trying to say is if you take, let's say, one piece of coal, and when you fall in, you hit the surface, so you can't go in. And you take another piece of coal with different shape and you again hit the surface and you can't go in. I don't actually know if there is a sense in which you can average the states and say, hey, now I can float freely into this piece of coal. So I think it would be interesting to know, so the fuzzballs are just behaving like pieces of coal. They have extra properties like, the entropy, which is high, like the Becquerel entropy, and they have certain properties. But apart from that, if you just think of a stat-mech system, it would be good to see if one can make a toy model where you can't go into one pure piece of coal, you can't go to another piece of coal, but somehow you can freely float into the average of the pieces of coal. So I've not quite ever understood if one can do that. And I'm concerned that at least that you can't do. I think one is talking maybe more of trying to find some correlation function, but let me really press the question on you that do you really think that you could get a horizon that you could smoothly float into, or where you could then naturally create entangled pairs? I'm just talking about the actual Hamiltonian at the horizon being smooth, the vacuum being the actual vacuum. Is there some sense in which one could do that for maybe a piece of coal? So
I think there's one important difference, right, is that there's a very specific entanglement structure across a surface in space, and that gives rise to some spectrum of the density operator on one side, which is shared by the radiation that comes out of a black hole. And it's it's that feature which, for example, is exploited in approaches like Papadopoulos Raju and ER equals EPR, which I think would not generically be shared by the radiation coming from a piece of coal. So there's at least a shot that you have in gravity, I think, that you don't have for the coal, though I'm skeptical, as you may, but I think there's an important difference.
Yeah, you even have to break the global symmetry. You really have to take throughout to get right entanglement structures between exterior mode and the rest, including Boltzmann coefficient of the sum-free double states.
I just want to ask a question to Samir and maybe Rafael. You see, that just statistical mechanics tells you that if you, so this is slightly different from the ensemble average question, but if you really were to take like a superposition or a typical pure state, the experience of an infalling observer in one typical pure state has to be exponentially close to the experience of the infalling observer in another pure state. I mean, that's just because it's a large system, and so all these observables have to be within e to the minus s of each other. So there must be some universal geometry that describes the experience of the infalling observer. It can't be all discrete fuzzballs which describe this. And so the question is, if that universal geometry is not the conventional black hole, what is that universal geometry? Because there must be some universal geometry just by statistical mechanics for a typical pure state.
I could tell you what I think would happen with the fuzzballs. And first, let me actually say that if you have a quantum system and you want something to be similar, I think you're really asking the question at a quantum level. And if you take a single spin maybe, and you send it into two different glasses of water, I don't think the evolution of the spin is the same, even though the water is a big system. In one, it may flip up, down, down like this, and the other, it may go up and down in a different way. If you ask a bad question, like what's the average value of sigma z, well, then you'll get the answer in both cases, the average value is 0. But that's not the actual question we should ask. We're actually asking if, I carry a spin in, will it really stay in the state, and can I do the interference things I would do with two spins and so on. The way I think it would actually work out with fuzzballs is if you actually went inside a fuzzball, started knocking around, two different fuzzballs would look as different as two glasses of water, and then you wouldn't have seen anything. But I think the way that this fuzzball complementarity ideas we were trying to develop would work, in case they were correct, is that if you throw in something with high enough energy, it's not the original fuzzball that you actually end up exploring. If you add an energy E, you actually create new fuzzball states, because density of states is very dense. In fact, you create new excitations, which, by the way, are not entangled with anything because you just created them and they've come with extra energy. And the evolution of this new part of phase space, that can be universal. So the idea of the fuzzball complementarity was, if you come with enough energy, you are creating new excitations, which are motion on a space of configuration, which were not right now occupied. So the fact you've gone from energy E to E plus delta E is the delta E, the new degrees of freedom, which are having a universal evolution. And so delta E being much bigger than T was important and was the approximation. So I think I'm just answering your question at two different levels. If a spin goes into a glass of water, I don't think just because a glass of water is big, it sees the same thing in both cases. So that's how I'm going to define the problem. But the reason it can still do it in the case of the black hole is that because the spaces are states are so closely spaced, you don't actually end up exploring the fuzzball you had that you fell into. When you bring the energy E in, you actually create a whole band of new states, and it's the evolution of those new states, how the wave functional spreads over that new phase space, which I think can be universal to a good approximation. And that was the idea of fuzzball complementarity. We don't know if it is true, but you can make a bit model exploring that. Okay? We made a bit model which does that, but I don't know if that is reproduced by actual fuzzballs. Okay, that's all I had to say. Maybe Rafael has some comments.
Well, I would say that I agree that I would expect an infalling observer to experience in a coarse-grained sense more or less the same thing, no matter what state the black hole is in. But I think the question is whether that thing is a smooth fall across the horizon or going splat on a firewall. And I think the key difficulty is that the vacuum at the horizon is a unique state, but a black hole and its radiation should be able to correspond to either the A/4 state. And so it's very easy to get the same experience for every observer if they go splat on a firewall, because there's presumably, if they exist, many different ways of making one. But it's very difficult to arrange for that unique state that you need at the horizon for an infalling observer to arise when there are so many different states for the black hole, as you know very well. But that's how I would, yeah.
But I think horizon could be unique at the coarse grain level. In other words, at the semi-classical level, you have a parameter m, which is even continuous. So it's not even e to the A/4. You have continuously many different black holes. That's right, A/4, A blank square, h bar is denominator. So if you go to the classical, e to the A/4 is a different mass, continuous mass even. And that all looks like a vacuum at the coarse grain level. It's not sensitive to the detail value of m. That's.
I have an outsider question for the experts here, if I may. How literally or seriously should we take this averaging that goes outside the main framework? Should we take it literally? We just have to average? Or should we view it as kind of a temporary caricature of what will eventually replace it? The example that comes to mind is the Bohr atom before the Schrödinger equation. So is this something like that, or should we take it more literally?
One possible answer to this question is that it depends on which theory we're talking about. And for some theories, we're supposed to take it literally. And for other theories, we're supposed to improve our understanding later.
I don't understand what it means. There is the ultimate theory of gravity. If people study that, say, in 100 years, how do you think, what's your view now, the way they will view it, say, in 100 years? This was a step in the right direction, but there isn't really an ensemble of theories, or yes, there's an ensemble of theories and a complete picture with a unique theory before that point was completely wrong. Which of the two options you think will materialize? You might also say that you don't know what will happen.
I guess I'm trying to reject your two options. Like, I think it can happen both ways. So there can be theories of gravity that make sense, where there's an ensemble. Maybe they're very rare, but there are some. JT gravity is an example. And there are theories of gravity that do not have an ensemble, like the dual to n=4 super Yang-Mills. So for the theory of gravity that's dual to n=4 super Yang-Mills, the ensemble is not the right answer. And I'm not sure if we'll later think of it as a first step in the right direction or something that was a little bit misleading. Time will tell.
Are the theories of gravity with the ensemble, are they theories of quantum gravity? Is it quantum mechanics? Is there a quantum state that evolves, or is it something different?
Yeah, it's a theory of quantum gravity defined by the path integral. If
I
you'd like.
don't understand this discussion. I was following the whole day, and at the beginning of this section and earlier today, there was a whole discussion, especially from Andy, whether we need string theory or not, and there's a unique theory of quantum gravity or not, and to what extent this depends on the microscopics and all that. And now your answer is, well, it depends on which theory of quantum gravity. So I don't see how these two parts of the discussion can be simultaneously correct. Now, my understanding is that in ADS, this is one particular background, and it might be that one particular background is easier than other particular backgrounds. But I don't think that we need an ensemble in some theories of gravity, but not in others. But what do I know? I'm an outsider here.
Nati, would it help if we made a distinction between whether an ensemble could exist as a mathematical duality that is interesting to study, such as the kind of things that were studied by Sachenko and Stanford, versus what the actual theory describing nature is? In other words, if you make a black hole in your living room and you want to know, you want to describe the radiation that comes out, personally, I would expect that that should be described by a single unitary theory. I have no idea what it would mean for the real world to be described by an ensemble. But it seems like we're learning a lot by studying models in which such a duality can be made fairly precise.
Perhaps we could go to some of the hand-raised questions. Seth Catalano has his hand raised for a while. Seth, you can unmute yourself.
All right. Hello. This is to anybody that would want to answer, and it relates a bit to something that had been talked about earlier. But I was wondering what you all think about whether or not we should try to be incorporating ideas from other quantum gravity frameworks, such as the idea of manifest background independence, or using a connection as the fundamental object rather than the metric when we develop our quantum theories of gravity? Or is there reason to believe that these are dead ends still in 2020?
I would like to mention on one idea for quantum gravity that had been proposed in the past by Gurau, for example. And that idea then got incorporated in our current understanding of the SYK model. It's closely related to tensor models and the SYK model. It might be that some other ideas that are floating around of quantum gravity can be incorporated in some way, maybe reinterpreted as necessary. Probably we'll also have to reinterpret string theory in the future.
And you say that was who?
Razvan Gurau.
Okay, thank you.
One comment I would make is that I think the path integral calculations are manifestly background independent. You know, certainly if you're doing full gravitational path integral, you're fixing the asymptotic boundary conditions, but other than that, you don't have a background geometry.
For that matter, string theory is background independent. You calculate the S matrix in an asymptotically Minkowski spacetime, and the definition really depends on the asymptotic geometry. Everything is fluctuating inside.
Wait, I'm sorry. Can you repeat that? Because if you're using a background to initially
put
the model.
What's correct? Let's discuss general relativity before we just classically. What's correct is to define the asymptotic background, and then you consider anything that can happen in the interior given that asymptotic background. What people usually call string theory in Minkowski space is really string theory in an asymptotically Minkowski spacetime. So it's misleading to characterize it as not being background independent. It's background, it's the correct treatment with that asymptotic background. On another point that was raised, the question of whether one uses a first order or a second order formulation is technical. It's not a conceptual difference. So on the scale of things that have been discussed by the panel today, that's a kind of infinitesimal difference, or one or the other might be convenient for some purposes.
I see. Okay, thank you.
I guess Raju is next.
Yes, I wanted to ask about the singularities. In particular, so we've learned that we can compute trace rho log rho using these replica wormholes, but all indications are if you wanted to compute like rho ij, where I and j are specific, Bryan-Ket indices for the density matrix, you will not get this from the replica wormhole. So does the singularity have to come in at some point in these calculations? And the second part of this question is, in the spirit of what Andy was saying, in string theory, do we have a slightly generic mechanism for resolving singularities? It seems like there are specific instances of how we can resolve them, but is there a sort of a more generic mechanism in string theory to resolve singularities?
I could comment on that. I think there's very noticeably not a general mechanism for resolving the Schwarzschild singularity. It would be interesting if there were. There's some singularities. There's a lot of singularities that we've had great success in solving. But that, of course, is a question that you would expect to need microphysics to answer.
Right. So I would expect that
it's a good sign of whether you have a good microphysical theory or not, whether it can resolve the singularities. And the failure of string theory to resolve the Schwarzschild singularity is, or to say much new about it at all, of course, is one of the things we have to deal with.
But Andy, string theory can resolve the singularity of extremal black holes, which is behind the horizon. So we know very well that the way singularities are resolved, a la Polchinski-Strassler and Klebanov-Strassler, in exactly the same way, the singularity of extremal black holes, which is behind the horizon, can be resolved by string theory, and it's exactly the same mechanism. Branes and fluxes and topology change. So given
those are time-like singularities. So there have been spectacular successes in resolving a huge host of disparate time-like singularities. And I think it's one of the best reasons we have for having confidence in theory. What?
But the Schwarzschild singularity with one electron, it becomes time-like. If you throw one electron into Schwarzschild, it becomes time-like. So it's not, it's only space like when the charge is exactly zero, but just throw one electron.
You perturb that a little bit and it becomes null. So
I know, but time-like
horizon. So I think it's a different story. Anyway, whether it's different or not, it's one that hasn't been.
I think it's interesting that these theories that have ensemble averages that are well understood ensemble averages like JT, they don't have a singularity.
But do they go through phi equals 0, those theories? Most of those theories are, phi is integrated out at the beginning, and the singularity that would be the relic of the higher dimensional singularity would be the thing at phi equals 0, and that's sort of thrown out from the beginning, right?
It's really phi equals minus infinity.
Yeah.
Yeah, it's thrown out, but the reason I make the point is that perhaps understanding this issue of ensemble versus non-ensemble will teach us something about the singularity.
I see.
Yeah, right. I guess the question is, are the quantities which are non-self-averaging intimately related to the singularity in some sense? Like the individual matrix elements of the density matrix or the S matrix.
I'm not sure.
Okay, thanks.
Well, let's move on to Steve Giddings, who seems to be next.
Thanks. So coming back to this question of ensembles, and this goes back to Nadi and Sandip's question during Douglas's talk. So if the ensemble story is like the old alpha parameter story, then you can focus on a member of the ensemble, which corresponds to, in that case, just having a particular set of couplings. And then within that member of the ensemble, you're back to the original question, how do you describe the unitary evolution in that member? So in a sense, you don't have to worry about the ensemble once you've done that. You forget about it, but you're back to the original problem. And then the problem is, how is evolution unitary? In the conventional description, you have the black hole subsystem. It builds up a huge amount of entanglement with the outgoing radiation. And the big question there is, how does that entanglement transfer out? I've argued small interactions can accomplish that. We can debate that. But then, if you're going to take the point of view that there's an island story, that looks like some other re-identification of the black hole subsystem or part of it with the outside radiation subsystem. And then there's the question of how you make sense of that in that context. So I'd like to just maybe throw that out and pose that partly as a question there.
I think what they might be doing that's different than what we did back in the 80s is, we just we used the kind of zeroth order approximation. No couplings between baby universes and no coupling between baby universes and other things in the geometry. And I've tried to reinterpret what they've been saying as, if you do a very special measurement, you'll couple more to you'll couple more strongly to a baby universe, and that can grab some information out from behind the horizon. But those are just words.
The simple ensemble story I was just referring to, it's true, involved ignoring baby universe interactions, and you and I considered other aspects of baby universe interactions.
Yes, we did. Yes.
But it's not really clear that that's sufficient to give the extra juice to this story to make it run.
But that could be said about anything. It's not really clear could be said about almost any statement in those follow-up papers.
Okay, but in any case, if one wants to make a claim that that's going to solve the problem, it would be nice to understand that.
Yeah.
So I'd just like to emphasize once more, I think, related to what Steve said. I don't think in this whole story there should ever be a need for adding interactions by hand that transfer the entanglement from the interior to the exterior. And I think that if there is this story of having to identify degrees of freedom in one place or the other place, I think, as Samir also emphasized, this is something that should work even in the absence of black holes, and I think it does. And I think it's something that we can examine even in empty space, even about the ADS vacuum, where I think we understand things very well. And I think we should take that seriously and think of that as a physical model for what is happening about black holes as well.
I think in some sense you're arguing that a black hole is not really a subsystem, because if it is initially a subsystem that builds up a lot of entanglement with the outside, and if you want to get the entanglement out, you have to have some interaction that transfers it out. And I think it sounds like your arguments are saying it isn't really a subsystem, that really the entanglement or the information is encoded outside. I'm not sure if that really holds up when you look at perturbative construction of the dressing and so on. That's another discussion.
Well, I would say it's not an exact subsystem, but I mean, it is a subsystem to good approximation. But I think this goes back to the question that Samir was asking. I mean, if you start asking fine-grained quantum information questions, then sometimes these things that look very different might need to be identified. But then for a lot of coarse-grained questions, they're clearly separate. And I think there's no inconsistency in that.
I'm not sure who's assigning who speaks.
There's a question. There's a question from Andrea Pum about the averaging story on the chat. Maybe somebody wants to, I can read it out and somebody can.
Sorry, I have the hand up for something.
Sorry, okay, go Abhijit.
Yeah, sorry. This question is mainly for Edward. Slightly tangential, but I think still relevant for this discussion. In your paper on global gravitational anomalies, you talk about, you try to find a principle which will teach us what to include in the gravitational path integral and what not to. And the answer, part of this principle, I think that you deduce is the cluster decomposition. So, and from that point of view, the configurations that stand out are the ones that differ in exotic structure. So how do you think that discussion fits in this story where the gravitational path integral is performed with the inclusion of all sorts of topologies, not just topologies that could, you know, that are required by cluster decomposition?
Is Edward still there?
Anyone else has any comment also? It would be nice to hear.
Edward, I think the question was for you.
Is Edward still there?
Edward is muted.
What was the question? Sorry.
Hello, Edward. Should I repeat the question?
Yes, please. I can't hear you.
Sorry. Yeah, sorry. The question was that in your paper on global gravitational anomalies, you talk about cluster decomposition being one principle that tells us what sort of configurations to include and what sort of configurations not to include in the gravitational path integral. And the conclusion was that the configurations having to do with exotic structures, different exotic structures, are the ones one should include because those are the ones that are dictated by the cluster decomposition. So how do you think it fits in with this story?
Okay. What I said was that the most conservative interpretation was that exotic spheres had to be included because you could prove from cluster decomposition that they had to be included. I said that purely cluster decomposition doesn't tell us what else we should include. But by now it's clear that all kinds of other things should be included. Roughly speaking, everything.
Thank you.
Okay, Deepak, you have a question?
Hi, yeah, thanks. So my question is for Sovrat actually. The question is that, so your statement is that given observers sitting in the space-like slice at the boundary of the space-like slice in ADS, these observers can conduct measurements which will tell them about the state which is in the interior, in the bulk of the ADS, right? So the question is that if you want to conduct such measurements, right, you have to perform some sort of a computation, right? So, and those observers themselves are also part of the geometry, right? I mean, you cannot think of them as like external to the geometry in some sense. So the question is that, like, is there possibly a situation where there is some back reaction due to that fact, which might create an obstacle in your claim?
Yeah, I think that's a very interesting question. Actually, it's I think the kind of question we don't engage with enough, which is, you know, when we think of measurements in quantum gravity or in a cosmological setting, we don't have the nice separation that we usually have in quantum mechanics, where you have an observer who's, you know, making some measurement, and you have a clear separation between the observer and the system. And so the kind of question you're asking now is, you know, as I said, you could have these observers who live near the boundary and who make unitary manipulations and measurements, and they're able to get some information about the bulk. But you're right, one could ask questions about whether there is some uncertainty because of some necessary back reaction that appears or something like that. And that's the kind of thing you wouldn't worry about usually in quantum mechanics. You have a system, you make a unitary manipulation and a measurement, and you know, you don't worry about whether the fact that the detectors themselves are part of the system. I don't have a good answer to that, and I think it's an excellent question, and I think it would be great to understand how measurements work in a cosmological setting and how quantum mechanics works in a cosmological setting when the observer is part of the system themselves. I don't know, maybe other people have something to say about that.
May I make a comment?
No.
Sure.
Oh, I'm sorry, I don't know how to raise hand. So if there's people before me, please go ahead.
Go ahead. Say what you want to say.
Okay. Yeah. So about the observer thing, yeah, I think that's really important question, and just want to mention that I have a new work together with Xidong and Zhenbin Yang and Xiangnan Zhou, which appears next week, where we discuss this using some tensor network models and also in some gravity theory. And just, I think that the key point, for example, one example is, I think if we assume we can have a strong, we can have an observer that's very powerful, that observes arbitrary correlation functions in the island, in the entanglement island, then the entanglement island is not an island anymore. That's excluded from when you say you calculate the same region of Hawking radiation, which has this entanglement island. But if at the same time you can observe arbitrary things in the island, then that's gone.
So your paper will be out next week?
Yeah, hopefully Monday.
Awesome. Thanks. Thanks for your answer, Subra.
Daniel Hollow, you still got your hand up.
Yeah, I still have a comment. Is it okay if I make it? So I wanted to emphasize something that Juan mentioned also in his talk. So, you know, there's all these debates about, do you include the wormholes, do you not include the wormholes, and so on. But there's, to me, the same mystery has already been there all along with the Gibbons-Hawking calculation, where I think that, you know, we were discussing, is there input from UV physics or not? Well, if you really just tried to compute a partition function in the bulk using the Euclidean path integral in the standard way, then you would do a Euclidean path integral where the spacetime is a circle times something, and the circle wouldn't contract. That's how we compute partition functions in every other kind of physics, except for gravitational physics. But in gravitational physics, we somehow have decided that we're allowed to compute partition functions in a different way, where we allow the circle to contract, right? If we did that in a statistical mechanics system, people would tell us we were crazy. And I think that that is where one example of a situation where there really is some kind of input, we need some kind of input from high energy physics to really tell us that we're allowed to do that. We can of course assume it and see what we get, which is what we've been doing for 40 years. But I mean, to me, you know, the evidence that it's really right to do that is that there are calculations like the Strominger-Vafa calculation or an ADS-CFT, where you can see that the entropy you get from that saddle point is really the right entropy. And without any kind of input from the UV, I think it's just something that we're making up. I mean, we don't know whether that's the right, we're allowed to include contributions with that topology or not in a Euclidean gravity path integral, just from the bottom-up point of view.
But sorry, wasn't the fact that that calculation gave exactly the right answer for the entropy and showed that the pair of black holes were quantum correlated strong reason to believe that that was the right way to do the calculation?
I'm not sure. I could just say that since the circle contracted, it's clearly the wrong way to do the calculation, right? I mean, you know, I think we have to somehow put in some assumptions about what we think is reasonable. And I mean, you know, the way Euclidean gravity has always worked is that we do a calculation, and if we like the answer, we say, okay, we're going to include that saddle point. And if we don't like the answer, then we say, oh, it was crazy to include that saddle point. We shouldn't have included it. And the reason why we're in that silly state.
I don't think that, because you could pair create, cluster tells you you have to be able to pair create.
But you're imposing some
monopoles at the end of strings, right?
I think you're imposing a principle there of cluster decomposition, right? I mean, Euclidean gravity path integral, the word Juan used is oracle, right? It's an oracle, and we just kind of, we play with it and see what we can get by doing different things, and we try to make up a story that's reasonable. But I think that in the end, like with a real UV complete theory, right, it would tell us which configurations we include.
There's a general rule about computations in physics If you do an approximation and the approximation looks sensible and the answer turns out to be finite, then this is the right answer. If the calculation is infinite for some reason, it means that you did not take into account some physics that you should have taken. And I actually don't know of a counterexample to this rule. So I'm actually not surprised that if you do a sensible calculation that gives a finite answer, the answer is meaningful.
I agree with this.
And that also addresses some of the question to what extent we should be surprised by an IR computation being sensitive or not sensitive to a question that could depend on the UV. I hope I made myself clear, because from all the chat here, I realized that people did not understand what I said before. So I feel very frustrated. So I'm really hopeful that this was clear.
Yeah,
I can also add that what Hawking always said was, if you want to know why a classical black hole has an entropy and a classical soliton in any other field doesn't, you should just look at the fact that when you do this Euclidean path integral, the Euclidean time circle pinches off in the black hole, and it doesn't. So you don't have the product structure, and that gives you the entropy even for a classical soliton. So yeah.
Emil?
Yeah, so I just wanted to follow up on that. So the Euclidean calculations in gravity seem to know more than they should. They can compute the entropy microscopically. And the cousin of that calculation, for instance, is the Carty calculation of the entropy in a 2D CFT, right? Where you do some modular transformation and you look at some identity channel in the dual channel. It's not that the identity channel knows something about the microstates, it just knows how many there are. And so what I'm wondering about these more recent calculations is that the Euclidean calculations that are being done with replica wormholes and so on give us answers that are very appealing and seem to be tracking some details of the microscopics. And where we seem to kind of stumble is in trying to give those calculations a Lorentzian interpretation, because then that leads to islands and all these puzzles we've been discussing. So I'm wondering if there's some wiggle room to accept the Euclidean calculations as, knowing something about the coarse-grained features of the theory, but that we shouldn't try to put too much into them and analytically continue them to a Lorentzian slice where they seem problematic. So I'd be curious to hear panelists' opinions.
So I think that has always been my view, that the actual states of the black hole, they don't have any horizons, and they are then given by the fuzzballs. You can always take all those states. A state can be, you can think of it as Euclidean or Lorentzian, just a state. And then if you evolve them in Euclidean time and make a one loop path integral, okay, that will be some finite number. It's a normal states in a normal theory. And then this particular path integral may actually have a saddle point, which is then given by the Euclidean cigar geometry. And so that saddle point is fine, doesn't have the interior to the black hole. The saddle point can be used to compute this path integral. But then you shouldn't continue a saddle point back to the Lorentzian section, because it's not computing anything there. So I think that's when we make the mistake. In the Lorentzian section, they are all actually fuzzballs with no horizon. In the Euclidean section, you can define a one loop path integral, and the saddle point of that is the Euclidean cigar black hole geometry. But again, we never continue a saddle point to Lorentzian and ask, what does this guy mean? And I think exactly as Emil might be hinting there, I think that's where we make a mistake. If we analytically continue to the Lorentzian, we just get a tool. And I think whatever calculations we have seen sort of working with the Lorentzian geometry, it seems to me that they have always things which can be computed on the Euclidean side, like a two-point function, and then analytically continued to Lorentzian. So sometimes we say we've used the Lorentzian black hole and look, this particular two-point function of one scalar field on the left, one on the right came out to be correct. But then we should go and check if that was the same thing which would have worked on the Euclidean section and then analytically continued. Then it hasn't really come from a Lorentzian calculation. You continued both the geometry and the path and the operators, and so it worked out. So I think indeed it's the Lorentzian continuation to the traditional black hole, which I think is the problem. It creates the horizons, the information problem, the singularity, but I think none of that should be there.
I think there is an old calculation that was done by Oppenheim and Snyder of a collapse of a shell. And they shown that the black hole forms, there is an interior and so on, and there is no argument that this calculation is wrong. So there's no need to do some Euclidean computation.
There is, at least in collapsing M2 branes, there is, because there's a tunneling. You have e to the S possible states.
Well, this is a vague argument. This is a vague argument. I like to see a concrete calculation.
It's done. It's, I mean, if you take M2 branes and you look at them tunneling into bubbling microstate geometries, you can calculate and you find exactly e to the minus S tunneling probability for e to the S possible states. So the calculation is done for a toy model with collapsing M2 branes instead of collapsing dust. But the calculation is done. It's not, and it gives exactly what you want. And there's a very nice conspiracy, how things work and so on. So this is known. I mean, the Oppenheimer-Schneider calculation ignores quantum effects, which should be there. And again, the quantum effects come because you have a huge amount of microstates, and it's like this enhanced tunneling. So the Oppenheimer calculation is invalidated by this calculation directly.
So I'd just like to respond to what Samir said earlier. I mean, in fact, I think we all agree that none of these calculations are giving you watertight evidence that the interior is smooth. But I think a lot of these were, I mean, these ideas originally, I think, were really brought into relief with the paradox that Samir himself, set out, which is that if you look at degrees of freedom near the black hole, they look near the horizon, they look like they're entangled with each other, but it also looks like they're entangled with the radiation far away. And of course, one resolution to that is you could say, maybe the interior doesn't exist, or you could say the interior has another, the interior and the radiation in some sense have to be identified. And I think the fact that they have to be identified, I want to emphasize, I think there's a lot of evidence for that. And I think there's a lot of direct Lorentzian evidence for that. And I think that's also something we can see in the absence of black holes, that if you make suitably complicated measurements far away, you're able to, you could get these kinds of monogamy paradoxes. So I think, to the extent that these arguments suggest that, just this monogamy paradox is not a requirement for structure behind the horizon, I think to that extent they're persuasive. But I think, I agree that, and I think everyone agrees that they're not directly telling us that there is nothing behind the horizon. Maybe there's somebody could come up with some other argument telling us why there's something behind the horizon. But I think the monogamy paradoxes are addressed, and I think they can be addressed directly in a Lorentzian setting as well.
Okay. Well,
Okay.
I think we'll leave it there.
Okay.
9 o'clock in that time zone. So thank you very much for everybody who participated. And I'll hand it back to Jeff.
And thank you, Malcolm.